Filter banks are an essential element of most audio coders. So here we have a block diagram of an encoder and a decoder, and we see that we have our audio input, then we have our analysis filter bank, a perceptual model, quantization encoding, multiplexer, and then our bitstream output. On the decoder, we have our bitstream input, then we have our bitstream demultiplexer, inverse quantization, and synthesis filter bank, and then our audio output. So here we see our analysis filter bank and our synthesis filter bank. So filter banks, they can transform from time to frequency domain and vice versa. Our goal here is to have good filter banks and to compress audio signals. Our approach is to make use of redundancy and some irrelevant parts that are present on our audio signal, so we can use a redundancy reduction and irrelevance reduction. Let's remember that filtering is the equivalent of convolution. So a digital bandpass filter, for example, can be represented by the convolution of the audio signal x of n with the impulse response of a filter h of n with non-zero coefficients between 0 and L minus 1. So the output y of n is obtained by the convolution formula we have here. It's very common to see filter banks with downsampling and upsampling. So here we will take a look at the downsample convolution. So we downsample the filter or the convolved signal by n by keeping only every nth sample. Then we replace our small n by m times capital N in our convolution equation. So n prime now is the convolution sum index at the higher sampling rate. So now dy of m, and here is the symbol for downsampling. So we have now replacing in our convolution sum, in our convolution equation, and then we have now that m prime is the convolution sum index at the higher sampling rate. And we can simplify our notation. We will always define m as the index at the lower sampling rate. Now the upsampling followed by convolution. So for the synthesis filter bank, we first have upsampling followed by a bandpass filtering. So the upsampled version contains the samples of the downsampled version at every n sample and zeros in between. So here is the symbol for upsampling. And now the convolution of the upsampled version is given by this equation here. So the upsampled version of y is only non-zero for when its argument is multiples of capital N. And we have that n minus m prime is equal to m prime times capital N, and hence n prime is equal to small n minus m capital prime times n. And here m prime is the convolution sum index at the lower sampling rate. So now we have this equation here, and for the summation limits for m, we need to observe that g of k is only non-zero for the argument in the range of 0 to L minus 1. So hence we have these conditions here, and we can use the floor operation, rounding down, and the ceiling operation, which means rounding up, and finally we will have this equation here for y hat of n is the sum. Here we have m prime g of k n minus m prime times n, and here we have our region of the sum.